Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate combinatorics. This particular lecture is on the inclusion-exclusion principle and based on section 8.1 of my invitation to combinatorics. Common thing that we do in combinatorics is to count. One way to count a set of objects is to break it down into cases. That's something we sometimes call the addition principle. You have a set omega that you want to count the number of its elements, and you might break it up into a bunch of parts. For example, I broke up my set omega into A1, A2, A3, A4. Then you might count each one and add them up, and that will give you the size of omega. That is breaking down your count into cases, and that's something that we often do in combinatorics. But what if the sets you want to divide your original set into are not disjoint and overlap? How do we take care of that? That's the purpose of the inclusion-exclusion principle, to allow you to split up your sets into parts where the parts overlap. First, some notations. If you have a set S, we think of that as a big set, the ambient set, and a subset of that A, then the complement of A in S, which we write as A with a superscript C, is defined to be all those elements of S that are not in A. Now, one note of caution, in this notation, A complement, we're not mentioning the set S, but to make sense of A complement, you have to know what the ambient set, the big set S, is. Let's say that you have a set and A1 through AN are subsets of S. I claim that if you take the intersection of A1 complement with A2 complement with AN complement, count how many elements there are, and add that to the size of A1 union A2 union A3 union AN, you always will get the size of S. Why is that? Because if you look at the intersection of those complements, what you're counting is the elements of S that are not in any of the A's, or outside all of the A's. The A1 complement are those stuff that are outside of A1, but A1 complement intersection A2 complement is those things that are outside of A1 as well as outside of A2. So when you take the intersection of all of those complements, you get elements that are in none of them. And when you look at A1 union A2 union AN, you're counting elements of S that are in some of the A's, maybe one of them, maybe two of them, maybe five of them. Every element of S is either in none of the A's or in some of the A's, and every element of S will be counted exactly once. Before we do the general case, let's focus on the case of two subsets. So let's say S is a set and A1 and A2 are two subsets of S. Then if you want to find A1 complement intersection A2 complement, so those are the elements of S that are not in A1 or A2, the inclusion-exclusion principle tells us that you get the size of S minus the size of A1 minus the size of A2 plus the size of A1 intersection A2. One way to see that is by looking at a Venn diagram. So here's this set S, the big square is all the elements of S, and A1 and A2 are two subsets. And what do I want? I want the number of elements that are in A1 complement intersection A2 complement. Which ones are those? Those are the stuff outside. Those are the elements that are not in A1 and also not in A2. Those are the elements that are in A1 complement intersection A2 complement. That's what I want to count. What does this formula say? It says that to find the size of A1 complement intersection A2 complement, you take every element in S, but you didn't want the elements of A1, so you throw how many of those there are. You didn't want the elements of A2, you throw how many of those there are. But in doing so, you've thrown out the elements of A1 intersection A2, the part of the two circles that intersect, twice. Once when you were taking out the elements of A1 and once when you were taking out the elements of A2. And that's an undercount. You took those elements out twice. So you need to put one more back in of the size of A1 intersection A2 to get a correct count. This proof, as intuitive as it is, doesn't generalize if you don't have two subsets, but have 135 subsets. So we want to give another proof of this two subset scenario, one that will generalize. So what we want to prove again is that the size of A1 complement intersection A2 complement is the size of S minus the size of A1 minus the size of A2, but then we have to put back in the size of A1 intersection A2. So how am I going to prove that? One way to prove that is to say that the two sides of this equation are counting some elements of S and not counting other ones, maybe double counting some elements, maybe not counting some at all. And what we want to do is look at each individual element of S and convince ourselves that they have the same contribution to both sides of the equation. If they're counted once in the left side, they're going to be counted once in the right side. If they're counted 10 times in the left side, they're counted 10 times in the right side. If the two counts are the same for every element, then we know that the two sides are going to be equal to each other. We start with an element in S, and we say that it's either in A1 complement intersection A2 complement or it's not. If it is, then let's see what its contribution would be. To the left side, it's going to make a contribution of 1, because when we count the number of elements in A1 complement intersection A2 complement, we'll at some point come across X and we'll count it. So X will make a contribution of 1 to that left-hand side of the equation. But what about the right-hand side of the equation? The right-hand side has different terms, so we may or may not count it when we come across those different terms. We'll certainly count it when we come to S, because X is an element of S. But when we come to A1 or A2 or A1 intersection A2, X is in neither A1 nor A2, so it's not going to be counted at all in any one of those. So the net contribution to the right-hand side is 1, just like it was to the left-hand side. So this X, the one that's in A1 complement intersection A2 complement, will have the same net contribution to both sides. As far as this guy is concerned, these two sides of the equation are the same. Now, what about if X is not in A1 complement intersection A2 complement? Then X is not counted on the left side, because it's not in A1 complement intersection A2 complement, so we don't count it. But what about the right side? How could X not be in A1 complement intersection A2 complement? It's not there because maybe it's in A1, maybe it's in A2, maybe it's in both. If it happens to be in one of those A's, either A1 or A2, but not both, then on the right-hand side, when we're counting the elements of S, we'll certainly count this element X. When we count one of the A1 or A2, we will be counting this guy, but not the other ones. So we will get a -1 here and a -0, depending on which one it is in. But when we look at A1 intersection A2, we will not count it because this guy was in just one of the A's. And so the net contribution will be 0, and that will be the same as what we had on the right-hand side. But it might be that X is in both of the A's, in which case it will be counted in every one of those sides of S, size of A1, size of A2, size of A1 intersection A2. We will be counting it every single time. And so we will have a contribution of 1, -1, -1, +1, but that's also 0. So this X also gives us the same contribution to the left and the right. That's true for every element of S. Therefore, the two sides of this equation are equal to each other. We're ready to state and then prove the general case of the inclusion-exclusion principle. We have a set, just like we had before, but this time we have M subsets. We have A1, A2, A3, AM, and we want to count the size of A1 complement intersection A2 complement intersection A3 complement intersection all the way to AM complement. So again, we want to be counting the number of elements that are in none of these subsets. How does this help us in a combinatoric situation? These subsets could be the elements that have a certain property. You want to count some set, and the A's will be the properties that you don't want or you're trying to avoid. If you want to count the size of the union, A1, union A2, union AM, if you know the answer to this question, then you know that the size of S minus this is the size of the union of the A's from the slide that we had very early on. What's the answer here? The answer is you start with the set S, but then you say, I didn't want the stuff in A1, A2, A3, and so on, so I take them out. So I have M terms that I'm taking out, but I overdid it because whatever elements were in A1 intersection A2, we took those out when we took A1 out. We also took them out when we took A2 out. So we have to put one version of those back in. And we have to do that for every pair of I and J where I and J are not equal. So for every pair, we have to take one such intersection out. But then we have to worry about triple intersections. When three of these sets intersect, we have actually put back in too much. And we have to take out one triple intersection for any time we have three integers I, J, and K not equal to each other between 1 and M. But again, we might have taken out too much. We have to put back in some more. And so we keep putting back in, taking out, putting back in, taking out, all the way till we get to -1 to the M, the size of A1 intersection A2 all the way till AM. The summation signs should not confuse you. For each subset of size 1 of 1 through M, we have a term in that first sum. In the second sum, we have one term for each pair of elements in 1 through M, or a subset of size 2 in 1 through M. And for the third sum, we have subsets of size 3. For each one of those, we have a term. For the fourth term, which I didn't write down, we have one term for each subsets of size 4, and so on. Here's the formula again. This tells us how to find the number of elements that are not in any of the A's. Start with S, take stuff out, put back things in, take out, put back in. This is inclusion-exclusion. Note that, for example, if M is 3, we have 3 subsets. What does this expand to find the size of A1 complement intersection A2 complement intersection A3 complement? You start with the size of S, you take out the size of A1, A2, and A3, but you have overdone it. You've put back one copy of the size of A1 intersection A2, A1 intersection A3, and A2 intersection A3, but you have overdone putting things back, and you have to take back out one size of A1 intersection A2 intersection A3. If you write this for M equals 4 or 5 or 6, then it becomes a little bit hairy and not clear, and you would really want a proof. Note that how many terms are here is the same as 2 to the M. There's one term S, then there's M choose 1 terms of the size of the subsets A's, then M choose 2 terms for the pairs, M choose 3 terms for the triples. That's a 1 row of the carriage GR triangle. That adds up to 2 to the M. Or another way of thinking about it is that there's 1 term for each subset of 1 through M. Now let's try to prove it. We want to prove that messy formula on the top, and we're going to replicate what we did for the case of 2 subsets. We start with an X in S and see what its contribution is to the both sides of the equation and hope that they're the same. We've got to make sure that we go through every element of S. We start with an element of S that it's a member of none of these guys. Then we will look at elements of S that are a member of some of them. If it's a member of none of them, then its contribution to the left is 1, because that's exactly what we're counting, the number of things that are not in any of the sets A1 through AM. And so when we get across X, we say, we count that. We count it once. But what do we do on the right-hand side? On the right-hand side, we will count it when we count the elements of S, but we don't count it any other time because all the other ones are counting some elements of some of the A's, and this guy is in none of them. So the contribution to the right-hand side will be 1 minus and then a whole bunch of zeros. And so it will be 1 also. And these 2 1s are the same. And so we're happy. But what if Y is a member of some of the A's? And let's say it's a member of n of these sets. So Y is an element of n subsets, and n is some number between 1 and m. What will its contribution be to the left-hand side? It will be 0, because we won't be counting it because it's in some of the A's. But what about the right-hand side? We have to be a little bit careful. It's 1 when we count the set S. Surely Y is in there. It gets counted. What about when doing the minus the summation of A1, A2, A3, when we're taking those out? Sometimes we'll be counting Y, sometimes not. We will be counting exactly n times because it's in n of the subsets. When we go to the next term, we're looking at pairs and their intersections. This element Y was in n of the subsets. So there will be n choose 2 pairs in which it's in the intersection. So we will be adding an n choose 2. And then when we get to the triples, it's again in n of the subsets. And so we have n choose 3 triple intersections in which Y exists. So that's what we're going to be taking out. And then this continues like this. We get this alternating sum of 1 row of the carriage GR triangle, usually known as Pascal's triangle. But what is that? What happens if you start at the beginning of 1 row of this triangle and go 1 and then subtract and add and subtract and add, and so you will get 0. Why is that? This follows from the binomial theorem, because binomial theorem says that 1 plus x to the n is the sum of n choose k x to the k, and you can plug x anything you like. This is a finite sum. You plug in x equals -1. On the left-hand side, you get 0. On the right-hand side, you get the alternating sum of 1 row of the carriage GR triangle. And therefore, this is 0. This says that the contribution of Y to the right-hand side was also 0. And remember, that's what we wanted to check, whether or not the contribution of every element of S to both sides of that messy equation on top of the slide is the same. In this case, where Y is a member of some of the subsets, the contribution to both sides is 0. When it's the member of none of the subsets, the contribution to both sides is 1. So the 2 sides of this equation are equal to each other, and we have equality. So now let's look at a couple of examples. Let's say we want to count the number of integers between 1 and 10,000 that are not divisible by 2, 3, or 5. How are we going to do that? If you want to use the inclusion-exclusion principle, we would start with the ambience set. The inclusion-exclusion principle is also an example of what we call in mathematics a sieve method, where you start with a bigger thing and sieve to get to where you want to get. And in fact, this is reminiscent of the first sieve method that was used in mathematics, which is the sieve of Eratosthenes, where he used that to find primes. If you wanted primes up to 1,000, you start with 1 through 1,000, then you eliminate all the multiples of 2, you sieve those out, then you eliminate all the multiples of 3, and so forth. And at the end, when you're done with that process, you're left with the primes. You can think of inclusion-exclusion as an example of a sieve principle. So our big set is the set of the numbers 1 through 10,000. That's where we are trying to find integers in there that are not divisible by 2 or 3 or 5. Now we have to decide those subsets. So A1 is going to be those elements that are divisible by 2. The sets are going to be the stuff we don't want, because our formula tells us the stuff that are in none of the sets. So A1 is those that are divisible by 2. A2 is those that are divisible by 3. And A3 are those that are divisible by 5. And what we want is A1 complement, intersection A2 complement, intersection A3 complement, because we want those integers that are in none of these sets, and we want to count those. According to our inclusion-exclusion, we have to find the sizes of each one of A1, A2, and A3 and their intersections. What about the size of A1? How many elements between 1 and 10,000 are divisible by 2? Every other one is even and divisible by 2, and so that number is 5,000. How many of them are divisible by 3? It's every third one, but when you divide 10,000 by 3, you don't get a whole number. You get 3,333 and a little bit of a fraction. But that fraction just means that towards the end, when you went 3 more, you would get past 10,000. And so that remainder doesn't really matter. And that's why you want to do 10,000 divided by 3, but then take the greatest integer in that. And the floor is what we use in combinatorics for that. So the floor of 10,000 divided by 3 means you divide 10,000 by 3 and you take the greatest integer smaller than that number. And that's 3,333. But then how many of them are divisible by 5? That's 2,000. But we also need to find intersection. So what is the intersection of A1 and A2? Those are the numbers that are divisible by 2 and 3. Those are exactly the numbers that are divisible by 6. The number of those is, again, the floor of 10,000 divided by 6 is 1,666, assuming that I've done my divisions correctly. The numbers that are in A1 and A3 are exactly the numbers that are divisible by 2 and 5, and that's the numbers that are divisible by 10. So there's 1,000 of them. How many numbers are divisible by 15? A2 and A3, and there's 666 of them in that range. And finally, how many things are divisible by 2 and 3 and by 5? 2 times 3 times 5 is 30. So how many numbers are divisible by 30? And there's 333 of them. By the way, if these numbers were not relatively prime, you wouldn't just multiply them. You would have to find their least common multiple. So by inclusion-exclusion principle, the thing that we want, the size of A1 complement, intersection A2 complement, intersection A3 complement, what is it? You start with the size of the big set, 10,000. Then you take out the guys you didn't want. You didn't want the multiples of 2, 3, and 5. And now we know how many of them are, but you overdid it. So you have to put back those pairs of intersections. You put those in, but you've overdone that again. You get 2,666 is the number of integers between 1 and 10,000 that are not divisible by 2, 3, or 5. Another example, let's say that we look at the letters M-A-T-H-I-S-F-U-N. There's 9 of them. And we're asking, in those permutations of these letters, how many of them do not have the word math, is, or fun? Like you see none of those words as consecutive letters in the right order. So we say that S is all permutation of the 9 letters. And then we say A1 is the ones that have math as consecutive letters, because again, that's something we don't want. And A2 is the ones that have the word is as consecutive letters in the right order. And A3 the same with fun. And what we want is A1 complement, intersection A2 complement, intersection A3 complement. We want to know the size of that. How many elements of S are not in A1, A2, and A3? And we know how to do that if we can find the size of each one of these things. The size of S is 9 factorial because that's the number of permutations of 9 things. You have 9 choices for the first spot, 8 choices for the second spot, and so forth, 9 factorial. But what about the size of A1? If I want to find the size of A1, I will think of MATH as one letter. And I will say I've got MATH, and then I have 5 other letters, ISFUN. And I want to take MATH and ISFUN and find all their permutations. And so that will be 6 factorial because I've got 5 letters, ISFUN, and math, and I'm permuting them. I use the same argument for the other things. For A2, I treat IS as one letter. And so I will have a total of 8 things that I'm permuting, and I will get 8 factorial. For A3, FUN will be treated as one object, and I will have 7 things to permute, and I'll have 7 factorial. What about A1 intersection A2? Then that means that I'm treating math as one letter, is as one letter, and then F, U, and N as 3 other ones. So I have a total of 5 objects that I'm permuting because I want to see both math and is somewhere as consecutive letters in the right order. And so the number of ways to do that is 5 factorial. And you do the same thing for math and fun. That will be 4 factorial because you just have math, fun, and then I and S to permute. And A2 intersection A3 will be 6 factorial. And what about A1 intersection A2 intersection A3? Then you want math, is, and fun as single objects that you're permuting. So you just have permutation of 3 things, and that's 3 factorial. And now the inclusion-exclusion tells us how to find the number of words that do not have a math anywhere in them as consecutive letters in the right order. They don't have is and they don't have fun. You start with 9 factorial, the size of S, minus the size of the single sets, A1, A2, and A3, then adding back in the sizes of pairs of intersections of sets, and then taking out the intersection of 3 things. You do that and you get 317,658, which is over 85% of the possibilities. So most of the time, if you do this randomly, you will not see math or is or fun. One special case of the inclusion-exclusion comes often, and you can streamline things just a tad. Let's say you have a set, S, and you have M subsets. We make one crucial assumption. We assume that when we're finding the size of the intersection of K of these, that only depends on K and not on which specific K subsets we found the intersection of. In this case, we're going to define these new parameters. Alpha naught is going to be the size of S. Alpha 1 is going to be the size of A1, the size of A2, and the size of AM. We have assumed that these are all the same size. We're all assuming that all pairs of intersections have the same size, all triple intersections have the same size, and so forth. That doesn't happen all the time, but when it does, this is a good thing. So we call alpha 1 to be the size of any one of these. Again, we're assuming that they're equal, and alpha 2 be the size of the intersections. Again, all of the intersections, and we're assuming that they're all equal. Alpha 3 is going to be the size of all the triple intersections, which are equal by our assumption, and all the way till alpha m being the size of the intersection of all of them. What does the inclusion-exclusion principle become? When we want to find the size of A1 complement intersection A2 complement all the way till AM complement, we start with the size of S, that's alpha 0. But then after that, we have to subtract all the sizes of one set, but all of those are the same, and there's M of them. So that will be M choose 1 times alpha 1. When we get to pairs of subsets, we have M choose 2 of them, and each one of those sizes of intersections is alpha 2. So it will be plus alpha 2 times M choose 2 minus alpha 3 times M choose 3. And a typical term will be M choose K times alpha K, and it's going to be minus 1 to the K because every other one is plus or minus, and we continue like that. In this case, we don't have those summation signs, and things are a little bit more streamlined. Let's look at one example. Let's say I have 4 distinct walls in a ceiling, and I want to paint them. I have K colors, maybe K is 47, so I'm not going to use all of them. What I'm going to do is that every wall I'm going to give a color, and I'm going to color the ceiling. The only thing that I care about is that I don't want the bordering surfaces to have the same color. Like the ceiling comes together with this wall, I don't want the ceiling and this wall to have the same color. These 2 walls are coming together, I don't want to have them the same color. If I paint each one of them a different color, then they would be different, but I don't have to do that. For example, I could do the ceiling blue and then do 2 opposite faces green and 2 other opposite faces yellow, and that would work. And I want to know how many ways can I do that. The first thing we notice is that the ceiling borders all of the 4 walls. And so the ceiling will have to get its own color because it can't share a color with the other walls. And there's K choices for that. So as long as we figure out how to color the walls using K minus 1 colors, and so that the adjacent walls don't have the same color, then we have to multiply the answer by K. And we're going to use inclusion-exclusion principle. Always we have an ambient set, and subset are the things we don't want. S is going to be all possible colorings of the 4 walls with K minus 1 colors, regardless of whether or not they satisfy our condition. Among these would be the case where you paint all 4 walls green. That's not good because many adjacent things have the same color, but it's one way of coloring it. So S is all colorings. And then A1 is going to be those colorings where the north wall and the west wall have the same color. The walls here are distinct in the sense that I know this is the wall that has that window, that's the wall that has the door, this is the one where I want to put that painting on, and so forth. So each element of S is one way of coloring the walls, and elements of A1 are those ways of coloring the walls where the north and west have the same color. Likewise, A2 is going to be the ones where west and south have the same colors. A3 is going to be the ones where south and east have the same colors. And finally, A4 is the ones where east and north walls have the same colors. And these are the things that we don't like. So what we want to find, as usual, is the size of A1 complement, intersection A2 complement, intersection A3 complement, intersection A4 complement. Here, alpha 0, what is that? I've got K minus 1 colors. So I have K minus 1 colors for this wall, K minus 1 color choices for that wall, and so on, a total of K minus 1 to the 4th choices of how many ways to color the 4 walls. It's pretty clear by symmetry that the size of A1, A2, and A3, and A4 are going to be the same as each other. So what's the size of A1? We want north and west to have the same color. So we have K minus 1 choices for north and west. Then we choose K minus 1 for east and K minus 1 colors for the south wall. And so we get K minus 1 cubed choices. Alpha 2 is going to be pairs of intersections. So if you look at pairs of intersections, either you have two opposing walls the same and these two opposing walls the same, or you have 3 walls the same and then that 4th wall differently. In any case, you will have twice that you have to choose colors, either one choice for these 2 opposing walls and one for those opposing walls, or one choice of a color for the 3 that have the same color and one choice for the other one. And because you have to choose a color from among the K minus 1 things, you have K minus 1 square choices. And alpha 3, if all 3 of these are the same, then you just have K minus 1 because they're all going to be the same. And in fact, alpha 4 is going to be K minus 1 also, because regardless of whether or not you intersect 3 of these or 4 of these, it means that all 4 walls have the same color. And if all 4 walls have the same color, you have K minus 1 choices because you have K minus 1 colors. Why K minus 1 colors and not K colors? Because we've already used one color for the ceiling. So K is the number of ways to color the ceiling. But now we start using inclusion-exclusion to find out how many ways you can color the 4 walls using K minus 1 colors and our condition that adjacent walls don't have the same color. We start with the ambient space, K minus 1 to the 4th, that's alpha 0, but then 4 choose 1 times K minus 1 cubed. Again, this is because all of the subsets have the same size, and then plus 4 choose 2, K minus 1 squared, minus 4 choose 1, K minus 1, and plus K minus 1. And if you multiply this out and then factor it, you will get K times K minus 1 times K minus 2 times K squared minus 5K plus 7. This is a pretty amazing formula because first of all, it has a root when K is 0, 1, or 2. So because if you have 0, 1, or 2 colors, you can't color this room with the condition that you're given, and this will give you 0. But if K is 3 or 4 or 5, for example, it'll tell you how many ways you can color this room. I'm done with the inclusion-exclusion principle, but I want to point out that this thing that we just found is an example of something called the chromatic polynomial. And so you can think of that room problem in this following way. That dot in the center is the ceiling, and each one of those other dots, other vertices, correspond to one of the walls. And I have put an edge between 2 things if they share a border. What I'm really trying to do here is color the vertices of this graph. And the condition is that no 2 adjacent vertices have the same color. That's called the proper coloring. The proper coloring of vertices of a graph is an assignment colors to vertices such that no 2 adjacent vertices have the same color. The number of proper colorings using K colors is always a polynomial in K that needs a proof, and that's called the chromatic polynomial. We found the chromatic polynomial for this graph. We found that the chromatic polynomial is K times K minus 1 times K minus 2 times K squared minus 5K plus 7. And we did that using the inclusion-exclusion principle. In future lectures on inclusion-exclusion, we'll apply to finding non-negative integer solutions with certain restrictions, as well as to derangements and other forbidden positions. This is the end of this lecture. Like my video and subscribe to my channel if you would like to be subjected to math videos in your feed, and keep hydrated at all times.